Hello everyone, this is DSS Zindabad and today we are going to discuss the daily challenge of Leetcode, which is climbing stairs. Let's jump into the problem statement. You are climbing a staircase. It takes n steps to reach the top. Each time you can either climb one or two steps. In how many distinct ways can you climb to the top? Okay, so this is the problem statement. Let us take an example and understand the problem statement. Given this example, we are having a staircase which has n steps in it. So here n is equals to 3. That means my staircase has 3 steps. I am somewhere here on the ground, right? And I need to reach the top. I need to tell how many. That means number of ways which are distinct in which I can reach the top. So I think this is something similar to finding out the number of possible ways, right? Whenever we talk about possible ways, we talk about all ways. So that means which are all the possible ways I can use so that I can reach the top. And for reaching the top, I can do only two things. Those two things are either I can take one step or I can take two steps. So that means if I was on the ground, right, I can either take one step, come here, this is one step, or from ground I could have taken two steps and I could have reached here. I need to move in a way so that I'm reaching the top. This is the problem statement. Now let's jump into the approach. Talking about the approach, it is a very easy question, right? It is related to something Fibonacci series if you have worked upon it, but if you have not, no worries, we'll talk about it in depth. So basically, here we know that I've been given something like a staircase, right? And supposedly my staircase has 3 steps, and from the ground I need to reach to the top. Now I need to tell the number of ways I can do that. When we talk about number of ways, what things come into our head? The first thing that comes into my head is that I need to explore all the possible ways in which I can reach the target, right? So for reaching the target here, I know one thing that I can either have one step or I can have two steps. So I feel okay. When I have talking about all the possible ways, I know what is used. Yes, right. We use recursion. Recursion is very, very important concept in DSA. So we have to use recursion to solve this question. Why? Because we have to figure out all the possible ways, all the possible combinations that I can think of for me to reach from my ground to my top position. Right. So now let's talk about recursion a little bit. Whenever we talk about recursion, we have to talk about the base case, right? We have to talk about the recursion function, that how the function will work. So talking about the base case, I can understand that there might be scenario where n is just equal to 1. That means my staircase has only one step. So how can I go to one step? We can do that by moving one step, right? If you have to just take one step, how can you do that? Only in one step, right? And there can also be another case when there is no step. This is the first case. This is the second case when n is equals to 0. In that case also we'll return a 1. That if you are already on the ground and that is the step. So you can be here in one step only, right? So this is the base case for this problem. Now let's talk about the recursive function that we'll be following. Now what recursive function can be followed so that I can achieve what I require? Looking at this example, I understand that what I have to do is that suppose if I have taken at initial time, right? For example, let's talk about in terms of time, right? So at t is equals to 0, that means I was here on the ground. I can make two choices. My first choice is either you move one step or you move two steps. So I can go for either one of them. So I say, okay, for the time being, I'll go with one step. They're like, okay. So I came here. Now I'm standing on my first step. When I'm standing on my first step, how many steps are remaining? If I had n steps and I've taken one step, that means n minus 1 steps are remaining. So if somehow recursion through its mechanism figures me out these n minus 1 steps, I can tell you the answer. Similarly, if I would have not taken this one step and I would have gone with something like a two step at time is equals to 0, that means I would have been somewhere here, right? So if I have jumped two steps and I had initially n steps, how many more steps are remaining to tackle n minus 2? So I understand that my recursive function will have something like n minus 1 and n minus 2. And these will be the calls that will be made, right? These are the recursive calls that will be made, because I am telling recursion that this is the base case, that is if n is equal to 0 or n is equal to 1. In that case, you need to return a 1. I've discussed already why. Else, you figure me out how I will get these, right? I hope this approach is clear to you people. Now, let's quickly take this approach and try. So, talking about the dry run, we have understood that my recursive function looks something like this, that if n is equal to 0 or it is equal to 1, that means there is no step or there is one step, I am returning a 1. Else, I am saying you return me recursive function, like let us name it f, right? So I'm saying it, you return me fn minus 1 plus fn minus 2. That means number of steps remaining if I've taken one step, number of steps remaining if I've taken two steps. So this is my recursive code, right? So now let's take a dry run. Let's take this example, n is equals to 4. So that means my staircase now has 4 steps in it. And I'm standing somewhere here on the ground and I have to reach here on the top. Let's maintain a recursion stack space so that it is easier for us to visualize, right? And I'll also draw the recursion tree for you to understand how things are working. So I also have a main function, right? Because I have to call this function. What I'll do is I'll simply pass that n here is equals to 4. And I've just made this call and I'm saying just return me whatever this function provides me. So the first call that is made is f is equals to 4, right? From here, I'll come to this code segment. I'll check for this condition and I'll see no, my n is not 0, neither it is 1. So I'll move to the next statement. I'll come, right? And while I was doing that, my recursion stack space has stored 4 here, right? Because this is the one I'm going to work upon right now. So now I come to this line segment. I'll say return fn minus 1. So this is again a recursive call. I'll say, okay, n minus 1, that is n was 4, 4 minus 1 is 3. A recursive call for 3 is made. As soon as it is made, it is added into my recursion stack space. I have not popped out 4. Why? Because we have not completed the execution for 4. Okay. So it is still in my stack space. Now, again, I come back to this code segment and I'll check, no, my n is not either 0 or 1. So I'll move again to this line segment and I'll see that, okay, I need to go to a recursive call where my n decreases by 1. So I'll make another recursive call for n is equals to 2. It gets added into my recursive stack space, right? Then I'll come back to this recursive code segment again. I'll check the value of n. This condition does not satisfy. I go to the next condition. I'll go for n minus 1, that is 2 minus 1 is 1. Now, when I come to this recursive call again, and 1 is added to my recursion stack space alongside. So when I come to this recursive call again, now the if condition is valid because now n is equal to 1. So in this case, what I have to do, I have to return a 1. So from here, what I'll do is I'll return a 1. As soon as I've returned a 1, my 1 which was present in my recursion stack space pops out, right? That it says that, okay, I have completed my work. I am going out. I am no more in the stack. So now my pointer comes to 2, right? My 2 says that I have completed my part till here in this code. Now you have to work with this segment. So I'll say, okay, I'm standing on 2. The recursion call is made, n minus 2, n was 2, 2 minus 2 is 0. So f is equals to 0 is called, and the 0 is added into my recursion stack space. Now when 0 is added into my recursion stack space, I go to f is equals to 0 call, and I'll come to this function again. I'll say again this if statement is satisfying because now n's value is 0. So from here also I'll return a 1. As soon as I return a 1 from here, my call for 0 function is ended, right? And I am on f is equals to 2. And I feel even I've satisfied this condition and there is nothing else to compare. So I'll say, okay, 2, you have done your work. Your answer is 1 plus 1, that is equals to 2. So you will also be popped out from my recursion stack space. So my pointer goes to the next top element of my stack. I hope everybody knows that stack is last in first out, right? So now I am standing on my function call for n is equals to 3. My function call says that I have done my work till here. Now you figure me out this section of the code. So here what happens is, now we'll make another call from f3. It will say fn minus 2. So n's value was 3. 3 minus 2 is 1. So again a function call is made for 1, right? 1 is again added into my stack space. I'll quickly erase this so that we can easily keep writing the recursion stack space elements, right? So I come to function 1. I go to this function. I say, yeah, n is equal to 1. That's true. I need to return a 1. I'll simply return a 1, right? 1 gets popped out from my recursion stack space, and 3 gets answered 2 plus 1, which is equals to 3. And I see that it has also completed its life cycle. So 3 gets popped out from my code. Next, my pointer moves to 4. As soon as I come to 4, I understand that I've completed my work till here. I need to figure this out. So okay, I'll erase this a little bit. Okay, let's not erase it. Let's try switching it in. Yeah. So my 4 says, okay, I have completed this section. You figure me out this recursive call. So 4 minus 2 is again 2. 2 gets added into my recursion stack space. Now I'm on n is equals to 2. I come to this function, right? I see is n 0 or 1? No, we'll move to the next. Moving to the next, what I see is, and to quickly erase this, I'll write it here that my main function had called f is equals to 4 initially, right? So now I am on 2 and I see that it is calling for n minus 1. So these two, from f is equals to 2, another function call is made, that is f is equals to 1, where n is equals to 1, right? This is added into my recursion stack space. I go to this recursion call. I see n is equals to 1 satisfies the if condition, will return a 1. So I'll return a 1 here. Then I'll go to, as soon as I've returned a 1 here, I'll pop out 1 from my recursion stack space. Now my pointer is here on 2, right? My pointer is here on 2. So now 2 will say, I have executed this segment of the code. Figure me out this section. So I have satisfied this recursion call. Now I'll go to this section, that is n minus 2 recursive call. So 2 minus 2 becomes 0. Fn is equals to 0. Recursive call is made. It is added into my stack, recursive stack. Now the pointer is pointing to 0 here, right? 0 says I am satisfying the if condition, return 1. I'll say okay, I'm returning a 1. As soon as it returns a 1, we pop it out from the recursion stack space, and my pointer again is pointing to 2. 2 says I have completed all of my work, and it is 1 plus 1, 2. It also gets popped out because it has completed a life cycle. Now, as we can see in my recursion stack space, only 4 is left. So my pointer comes here, right? So now 4 is getting both the answers, and it is 3 plus 2, that is equals to 5. Hence, that means if I have a staircase which is having 4 steps, and I can only move in either 1 step or 2 steps, then I can do that using 5 different ways. I hope this was clear to you, right? So before jumping into writing this code, because see what I've written right here is the code itself, right? It is almost the similar code that we'll be writing, but this code will not work. Now, why is that? See, it was easy to have a dry run for a very small value like n is equals to 4, n is equals to 2 or 3 or something like that. But if the value of n is very big, so it is very hard. And there is something that we can see that we are recomputing things. Here I figured out f is equals to 1, f1, f1. See, I figured it out the very same thing 3 times. Again, my function is going and trying to figure out what is your value, what is your value. Similarly, here you can see f n is equals to 0, f n is equals to 0, right? So what are these? Why do we have these repeating function calls? These are known as overlapping subproblems. Okay. And whenever we have overlapping subproblems, then for optimization process, right? So as to optimize whatever code I have written, I go for something which is known as dynamic programming, which is DP, right? So basically what does DP does is, DP helps us store the pre-computed values, right? And it stores whatever has been computed in a block, let us assume. And it says, okay, don't recompute it again and again, that go to this, go to that. No, don't do that. I have saved it here, use it directly from here, right? So it optimizes the code. So for applying DP here, what we'll do is we'll simply have a vector DP, right? Which will be of int type, obviously. And talking about what will be its size will be n plus 1. And we'll initialize it with -1. That means that at that index, nothing is stored, right? So -1 indicates that nothing is stored right now at that index. If it is not -1, that means something has been computed and stored in that block. Talking about why n minus 1, see, we've been given that we are given n steps. So that means even n is inclusive. So in that case, because we know vectors work from 0, right? So as to work with n steps, we have to take n plus 1. Now I'll quickly code this up. Then we'll further talk about the time and space complexity. Before coding it up, there's one more very little thing that I like to point out. Alongside pre-computations, right, I told you that it helps, DP has something pre-computed stored and we can use it. But a lot of you can ask me a question, but why do we need it? We need it because the recursive solution that we just talked about had a time complexity of 2 raised to the power n, which is an exponential time complexity, and which is very, very big, and that is not required. Because here, if you see, we are having 2 different types and we are having these calls for n number of times, right? So that is why the time complexity is 2 raised to the power n. DP helps us to bring this time complexity to almost linear, right? Or at least n square or n cube, depending upon the problem statement. So that is why we move forward with DP for optimization. Now let's talk about the code, and then after coding, we'll talk about the time and space. Okay, so this was the problem statement, right? First, let's have the recursive code. So I know that I can create something like a function and I can provide it with n, and I'll say, okay, you simply return me whatever you have computed, and we can make int f function, and I'm providing it with int n. And as I say that if n is equal to 0 or n is equal to 1, that means no step 0 or 1 step in my staircase, then you return a 1, else you return f n minus 1. That I mean I have made first, I have, my first move was taking 1 step, figure out me the rest of steps, or n minus 2. N minus 2. Let's run it. I hope this should work fine. Okay, so as I talked about, if we have 4 steps, then we have 5 different distinct ways of reaching the top, right? Now let's submit it and see if this works. So as you can see, we got a time limit exceeded. Why? Because this code has a time complexity which corresponds to exponential, that is 2 raised to the power n. Okay, so this is not a good approach. What we can do instead is we can use something like dp, right? So for using dp, what I'll do is I'll say, okay, take a vector of int time, name it dp, give it a size n plus 1, and initially everything should be minus 1, and I'll also pass it into my function, that is f. I'll pass it by reference so that the changes can be made. Now I'll say that if at any point of time, so you need to understand this before talking about what all things will come here. You need to understand this. Why did we make 1D DP, not 2D DP, 3D DP? In this function f, right, only one parameter is changing, which is n, right? The size of DP always depends upon the number of parameters that are changing in the function. So in this function f, only one parameter is changing. That is why we've created 1D DP. So now what I'll do is in my function f, I'll say that check, is that value already pre-computed or not? That means if dp of n is not equal to minus 1, that means it has been computed. Then do not recompute it, simply return whatever is its value. Else, what you have to do is you need to store it at every point of time. So this gets stored here. We'll run it again. Okay, yeah. So here also, because we have changed the parameters, here also we have to pass dp. And it is running fine, but I don't think it will still work. We'll still get a time complexity error, I feel. Okay, it worked. It worked, but this is just one way of doing it. We can even optimize it further. Now, talking about this approach, what is happening is this is known as memoization, right? And it is a top-down approach. Basically, in this, what is happening is I've created a vector dp, right? And I am storing the pre-computed values so that it doesn't have to recompute the values over and over, right? So the other way, which is further an optimized version of memoization, is tabulation. So basically in tabulation, what we say is follow the bottom-up approach. So what is the bottom-up approach? It says that the memoization is a top-down approach. Why? Because if you see, we started from, if you remember, you can see that in this tree structure, I started from n is equals to 4. That is my top value, what I want to get as a result, right? So this is recursion and memoization is a top-down approach. Talking about tabulation, it is a bottom-up approach. Now, how can we write the tabulation? It is that whatever you have written in your memoization solution, just simply use that and start building from the bottom. That means whatever was your base case in the case of DP, in the case of memoization code, use it as your bottom and then build upon it. So now what I'll do is I can simply comment this out, right? Because this is the DP solution for memoization. I'll just quickly copy paste it here. Okay. Now talking about the bottom up approach, which is tabulation. I have created a DP vector and let us initially give everything as 0. There is no return statement anymore, right? So what I'll do is I'll say I know that the base cases in memoization was that if n is equal to 0 or n is equal to 1, in that case we return a 1. So here I'll say if dp index 0 is equals to 1, dp index 1 is equals to 1. And then I'll run a for loop. As I have worked with the indexes 0 and 1, my for loop will begin with index 2. It will run till n, right? N inclusive. And I'll simply say that put it in dp of I, whatever is dp I minus 1, that means one step, and dp I minus 2. You can completely relate the for statement loop using this. I have done nothing. I have just replaced f with dp, right? And I'm storing its value, and eventually I'll return dp index n. Let's run it. And we see it's working fine. Let's submit it. Now here, if you see, from having a solution initially, which was recursion, which was exponential, I got the solution, which is just a linear traversal, nothing else, right? How could I get this linear traversal was by understanding how memoization worked first. Now this tabulation can be made even more optimized. That can be through pointer approaches. Now, how can we know that when we can apply pointer approaches is by understanding if we have something like previous indexes, right? What is previous indexes? So what is happening here is, let me quickly copy paste this code and talk about it. Okay, so this was the code that we had just worked upon, right? So let us assume that n was equals to 3. I had a vector for size 4, right? That means n plus 1. So I have something like this as dp, which has 0, 1, 2, and 3. That means it is of size 4. Now, what I am doing is I am saying, okay, whatever is on the 0th index, put it as 1. And on index 1 in DPRA, put that value also as 1. Now, I am running a loop from this pointer and I'm saying its value will be equal to whatever is the sum of these two values. So, 1 plus 1 is 2. Then I am moving forward my iterator. I'm coming to 3 and I'm saying its value would be whatever is present in index minus 1, that is 3 minus 1 is 2, and index minus 2, that is 3 minus 2 is 1. So we'll add this up, we'll get a 3, and we'll eventually get 3 as the answer, right? So I understand that at each point of time, I just need two pointers. That is a previous pointer and we can say the last previous pointer. Basically, my previous pointer is storing what we can say what is at dp index 1, and last previous is storing whatever is at dp index 0. And rather than having this space complexity of O of n, I can have just two pointers, which will reduce my space complexity to O of 1, and my time complexity will remain as O of n, because I'll be still iterating over all the numbers to get n as the final output, right? So let's quickly code this up and understand. Okay, so I have talked about how we can use the two pointer approach, and through that we can space optimize this. So I can have a previous last, right? and let's initialize it to 1. What is my previous last? It was basically what was my dp0 storing, and I'll have a previous pointer that is also 1, and that is what my dp1 was storing. Then I'll run a loop, right? Int I is equals to 2, I is less than equal to n, I plus plus. I'll say I'll have an int current, which is equals to whatever was in my previous last plus whatever is in my previous. After that, I'll update my previous last with previous. I'll say put that value. And for previous, I'll say whatever is the current value that is computed, put this. And then we'll eventually return previous. Let's run this code. And it is working fine. Let's submit it. Okay. So for this question, for this code, we can see the space complexity boils down to O of 1. So do you understand? First, we had a space complexity of O of n, right? So I'll quickly have a comparison here. Okay, so let's quickly compare the codes that we have discussed. The first approach was through recursion, right? Here, the time complexity was exponential as we had two different ways in which the question could be solved. So we had time complexity of O2 to the power n, and the space complexity in the worst case scenario was O of n, because as you saw that we had a recursion stack space, right? And in the worst case, it could have stored all the elements. So from recursion, we went to a better optimized approach, that was memoization. Memoization is a top-down method. And as I've told you, we can simply use something like a DP vector, which is initialized with -1, and we can prevent recomputations through it. Here, my time complexity boiled down to O of n, and my space complexity still remained O of n. Here, now we had the DP vector that was created. After memoization, the third thing that we went forward with for better optimization was tabulation. Tabulation is a bottom-up approach. So bottom-up approach basically is usually developed using memoization. Whatever is the base case here, you use it to build through tabulation. Here, my time complexity again remained O of n, and my space complexity was also O of n because we had a DP vector here too, right? Then we move forward with space optimization because the time cannot be reduced any further. So we moved with space optimization. In case of space optimization, what I did was, rather than having a complete vector dedicated to storing the computed values, I was like, I know that for any index at any point of time, I just need whatever is the previous and whatever is the previous last. That means if I want to know for I is equals to 4, I just need to know what was the value for I is equals to 3 and what was the value for I is equals to 2. Similarly, if I want to know for I is equals to 3, I want to know what was the value for I is equals to 2 and what was the value for I is equals to 1. So I understand that I just need these two pointers, right? And if I'm computing I is equals to 4, I do not need what is there in I is equals to 1. So I moved forward with two pointer approach. And herein, my space complexity boiled down to O of 1. Why? Because I'm just using two pointers now. And my time complexity remained O of n. It is very important that if you get such a question in your interview, you tell the interviewer the complete thought process, starting from recursion, coding it up, telling and talking about the time and space complexity, talking about why memoization, why do you use DP vector, then talking about tabulation, and finally coming to space optimization. Thank you so much for viewing the video till the end. Please like, share, and subscribe. Thank you.